Hey everyone, it's Justin again. Up to this point, we've been writing all of our sequences using the same notations. The first term always occurs when n is 1. But in this video, you'll learn that there are other ways of doing it, and they all involve playing around with a domain. This can be a little difficult to understand if you don't know what sequences are, so you may want to review your other lessons about sequences before attempting this lesson. Alright, first off, how would you define this sequence? According to what you've learned so far, we would define it as any term equals 4 times 2 to an exponent of n minus 1. By plugging different values into n, we get different terms. The problem is, where do we start? In the past, we've always just let n begin at 1. Then n continues through all the integers. In this case, we would say that n is always an integer, because if we used a fraction or a decimal, we get a number that isn't part of the sequence. And n has to be greater than or equal to 1, because it starts at term 1 and goes up. But what if I told you that this isn't the only way to define this sequence? For instance, this definition can be equally valid. Notice that I said can be. There's a little more to it. If we just start n at 1, then the first term we get will be 8 instead of 4. So we need to back up. Instead of 1, n should start at 0. That gives us 4, and then as we continue making n bigger and bigger, it will generate the rest of the sequence. So in this case, n is an integer and is greater than or equal to 0. These are two different formulas that both create the same sequence, and the key is the domains. What about recursive form? Typically we write it like this. The first term is 4, any term is 2 times the previous term. In this case, n has to start at 1 because that's the given term. If it started at 0, then the given term, a sub 1, would be the second term in the sequence, and that wouldn't make any sense. But what we can do is intentionally define the given term as where n is 0, so that we can force the domain to start at 0. We could use any of these 4 formulas to create this sequence, as long as we're careful in following the domain. Okay, that was a lot of information, so let's move on to a new sequence. Pause the video and take a moment to figure out a formula for this sequence. Most likely, you wrote the formula like this, because this is how we've been writing explicit formulas for arithmetic sequences since the beginning of this unit. This formula requires a domain of integers 1 and above. If n is 1, then the 6 ends up getting zeroed out and only the 52 remains for the first term, so it checks out. We could also write it like this. Now the domain begins at 0, but that's okay because using 0 for n leaves just the 52. So the starting term will still be correct. Or we could do it recursively. Define it either with an initial term where n is 1 or where the initial term is term 0. For each of these 4 formulas, using the starting value for n will give you 52. And then increasing the value of n will return 46, and then 40, and then 34, on and on and on. They all work to generate the same sequence. You might still be a little confused, and that's totally understandable. It's difficult to imagine how one sequence can be written as multiple different formulas. So let's look at it the other way around. Here are 4 different formulas. 3 of them create the same sequence, but one of them doesn't. Can you find the imposter? Let's just start in the top left. The domain says that n starts at 1. This makes the exponent 1 minus 1, or 0, which means the 1 doesn't get multiplied by any negative 3's, making the first term just 1. If we bump the value of n up to the next integer, 2 minus 1 is 1, so the second term is negative 3. We can already see where this sequence is heading. The formula says the common ratio is -3, so each term will be multiplied by -3. The third term is 9, the fourth term is -27, on and on. Now let's check the top right formula and see if the sequence matches. This formula has a domain starting at 1, so we plug in 1 for n, and we get -3. Then we bump n up to 2, and we get a value of 9. From here, we can keep the pattern going by multiplying by -3 each time, -27, 81, on and on. This sequence is different from the first one. One of these must be the imposter, so let's check the other and see which one doesn't belong. In the bottom left formula, n starts at 1, and a sub 1 was given to us as being 1. Then for a sub 2, we multiply the previous term by -3 and get -3 for the second term. And the pattern will continue, multiplying by -3. Finally, let's check the bottom right formula. In here, n starts at 0, and a sub 0 is given to us as 1. The recursive formula multiplies by -3 each time, so after that we'll get -3, 9, -27, etc. So 3 of these formulas created the same sequence, while the top right one actually started the sequence on the wrong term. In order for this formula to create the same sequence, it would have to start a term earlier. In other words, the domain would have to start at 0, not 1. Sequences are a difficult concept, and it only gets more complex when you start messing with domains and writing the formulas in different ways. When in doubt, plug in integers for n, starting wherever the domain starts. If you're still struggling, try practicing on our website. See you later.